Welcome to the debate. For this episode of Phil's podcast, we're asking the question, does anyone really know how an LLM works once it's been fed, just tons and tons of data? They say even the designers don't fully get the logic behind it. True or false? We're diving into it on Le Podcast de Phil to understand what's happening, especially with tools like NotebookLM helping us break it all down. So, today we confront a fundamental question driving the evolution of artificial intelligence. We often hear this claim: once a large language model has consumed massive amounts of data, even its designers don't truly understand its core decision-making logic. Is that opacity an unavoidable reality, or is it actually a challenge being systematically overcome? The central question really is this: is the inherent black box nature of LLMs an unbreakable barrier that keeps their internal logic fundamentally unknown? Or do our modern methods of audit and control actually provide a sufficient, a working level of understanding for safe deployment? I'll be arguing that this opacity is indeed fundamental, and the core decision logic of these models remains, frankly, dangerously unknown to their creators.
And I'll be taking the opposing view. While yes, the massive scale of the parameters means we don't track every single individual detail, I maintain that our knowledge of the architecture, combined with advanced techniques for traceability and alignment, gives experts entirely adequate functional comprehension and control.
Right. So the claim that designers lack full comprehension post-training, it isn't hyperbole. It is really a description of the system structure. We are dealing with models built upon billions, literally billions, of statistically adjusted parameters. They are expert pattern matchers, learning immense correlations from text, but they don't possess genuine comprehension or conscious reflection. The opacity exists because the intermediate layers, the sheer depth of the neural network, make it basically impossible to provide a precise deterministic account of why a given output was selected over another. We are left operating a system whose complex internal rules are structurally obscure. And this lack of deterministic understanding poses non-trivial risks: unpredictability, persistent bias, hallucinations, which, frankly, external controls alone are simply insufficient to eliminate.
I find that perspective overly pessimistic because it seems to conflate scale with mystery. We may not track every single parameter, okay, but that misses the crucial point. We know the mechanisms of learning and operation. We understand the transformer architecture completely. We know precisely how the attention mechanisms allocate weight to different parts of the context. We control the process of embedding. And maybe most importantly, we dictate the training process, including that critical alignment phase, using reinforcement learning from human feedback, or RLHF. So my argument pivots the discussion away from this maybe unattainable total internal comprehension toward effective control and observability. We implement systematic audit procedures, distributed tracing, and real-time surveillance. These rigorous frameworks demonstrate that we can enforce ethical alignment, guarantee safety, and manage the technology reliably, even with its computational vastness.
Okay, but I want to challenge a reliance on mechanism over function here. You emphasize the architecture, the inputs, the structure, but the function remains profoundly alien to human reason. You can know every wire in a house, but that doesn't tell you why the resident chose to paint a wall a specific color. The internal logic is purely statistical. When an LLM performs something like chain-of-thought reasoning, it isn't reflecting. It's executing complex statistical reproduction based on patterns in its training data. Because this logic is purely mathematical, it's devoid of human traits like emotion, conscious reflection, or a stable identity. It operates on principles fundamentally outside human intuition. The mere absence of human-like cognition confirms, for me at least, that the internal processes remain opaque, regardless of how high quality the output might appear to be.
Well, I think the analogy of the house wiring is a bit misleading. We don't need to know the model's emotional state because, it doesn't have one. We need to know its mechanical state. Knowing how the attention mechanism weights context and knowing how those weights are systematically adjusted through training, that is the crucial knowledge. It means we understand the system's decision boundaries, or at least how they're formed. And the existence of RLHF really proves this point. We use targeted human feedback to refine and align the model, systematically adjusting its behavior towards safety and utility. Understanding the architecture and the training adjustment process means we understand the lever points of the system. We know how to influence, constrain, and direct the model's behavior. So why isn't knowing the lever points sufficient for safe deployment?
Because the levers are constantly slipping, or perhaps we don't fully understand all of the levers. This brings us to the core problem of interpretability tools. You argue that these tools give us control, but they're generally deployed after an error occurs, or they often only work effectively in narrow research settings, not necessarily in the wild. When we talk about critical applications, legal drafting, medical diagnostics, financial analysis, the potential for unpredictable error, bias, or outright fabrication remains high precisely because the internal mechanisms are opaque in novel situations. Audits and tracing procedures are fundamentally retroactive diagnoses. They help us understand what happened or why it went wrong in the past.
Sure.
But they don't solve the core issue of inherent unpredictability. When the model encounters novel contexts or receives a subtle, perhaps adversarial prompt, this partial opacity requires constant human vigilance. We simply cannot place blind trust in the system because we can't predict its behavior in all possible scenarios.
I'm not convinced that you're fully appreciating the sophistication of modern interpretability tools. We are moving far beyond simple input-output logging. We are actively probing the neural core, and these methods are not merely retroactive. They are diagnostic and increasingly predictive. For instance, we use advanced visualization techniques like heat maps to see which sections of the network are activating for specific tasks. More critically, we employ perturbation analysis. Now, this involves injecting controlled noise or targeted changes into the system to measure how the output varies. It is essentially giving the model a controlled poke to determine which individual neurons or subnetworks are most responsible for a specific decision or output. This allows researchers to rank the influence of specific components. We also use causal tracing to verify the exact causal pathway between activation and the final result. So these methods combine sensitivity measures and graphical insights to provide transparency into the decision-making path, not just after the fact. Furthermore, mandated systematic archiving of all inputs and responses ensures that every decision chain can be rigorously followed and diagnosed, pushing the needle dramatically away from the true definition of a black box.
Okay, but if you have such advanced control, then why is constant, expensive external management necessary? The need for continuous fine-tuning, rigorous access restrictions, and external security measures, or safeguards as they're sometimes called, is, to me, the ultimate proof of internal instability and a lack of true comprehension. I mean, if we genuinely understood the deterministic logic governing those billions of parameters, why would we need perpetual interventions? Why would prompt injection or data poisoning remain such persistent, serious threats? Relying on continuous auditing and access management feels like an unavoidable admission. The sheer internal complexity is beyond the developer's complete grasp. We are managing a powerful, volatile force using external restraints, which is, let's be honest, far different from having mastered its internal physics.
That's a logical jump I can't quite follow. You seem to be setting an unrealistic standard, absolute deterministic certainty, and framing anything less as a failure of comprehension. Security and ethics demand layered controls for any complex system, whether it's a high-frequency trading platform or a nuclear reactor. The fact that we implement fine-tuning, RLHF, strict access controls, and ongoing penetration testing doesn't prove we don't understand the model. It proves we are deploying it responsibly. We understand the learning process, which is arguably the most critical piece of the puzzle. We know where and how to apply pressure to guide its outputs. We use sophisticated prompt engineering techniques like chain-of-thought decomposition, which force the model to break down its reasoning into verifiable steps, leading to more controlled and safer outputs. We even use secondary LLMs solely dedicated to evaluating the quality and safety of the primary model's responses. This layered approach successfully mitigates risks and ensures ethical, secure usage, making the technology reliable and deployable, irrespective of the, let's call it, lingering opacity concerning every single parameter dynamic?
Well, I maintain that while the high-level architecture is known, the vast statistical complexity embedded in those parameters means the definitive internal decision logic remains fundamentally opaque to us. The structural reality demands continuous regulatory caution and constant human oversight, because the inherent risks, unpredictability, and latent bias are real and, frankly, built into the fundamental nature of the system. We must proceed with humility, understanding that we are managing a complex system whose inner workings we cannot fully predict.
And I would reaffirm that while total knowledge of every parameter might be an academic ideal, we possess a sufficient, functional understanding of the key mechanisms, the attention system, the training process, and, critically, the alignment phase, coupled with sophisticated control techniques like deep neural analysis and systematic tracing. This combination allows experts to reliably harness and regulate LLMs. The black box is not an unsolvable mystery, but rather a manageable engineering challenge we are actively tackling.
And the tension between the incredible utility of these systems and their residual internal opacity is precisely what continues to drive essential research in interpretability and security today.
Exactly. Ultimately, the debate is probably less about achieving total, perfect knowledge and more about establishing responsible, effective control that allows us to safely utilize these transformative tools.
This discussion was made possible by the materials summarized by NotebookLM. We invite you to join the growing community of listeners of Le Podcast to Philip. Please help us reach 2,000 subscribers and share this content with your network.